Hello everybody, welcome to the International e-seminar on control systems. Umar, are you with us?
Yes.
Okay, so this seminar is hosted by the chair of mechatronics in Technical University of Kaiserslautern, and the research of our group is concerned with control and dynamical systems, and it's organized into three main pillars, namely hybrid systems and cyber physics, complex dynamical systems, machine learning and control. In addition to control theory, we are engaged in modeling analysis and algorithms designed for dynamical systems in various scientific and engineering disciplines like cyber physical systems, autonomous and cooperative systems, energy and demand side management, smart logistics and production, particle populations and process control, and computational system biology. So this is a monthly seminar, um, and because of the Christmas, this is going to be the last seminar of this year. So we will resume this international e-seminar for the next year. So today's talk is on modeling and control of COVID-19 epidemic through testing policies. And the speaker is Muhammad Umar bin Niazi from GIPSA Lab, and he's also affiliated with INRIA Grenoble Own Helps. So about the speaker, Mr. Umar bin Niazi is with the Grenoble, University of Grenoble Alps, and is affiliated with GIPSA Lab and INRIA. His research interests include large-scale network system, aggregated state observers, model reduction, and differential game theory. It is important to emphasize here that Mr. Niazi was a finalist for the Best Paper Award in European Control Conference 2019 that happened in Naples, Italy. And he's a very nice colleague, and we were neighbors as well during my short research visit to INRIA Grenoble. So now I will give the floor to Umar Niazi, and I wish him good luck for the talk. And we are having a big gathering of participants here from all over the world. So good luck for your talk, Umar.
Thank you very much, Said. Thank you for the nice introduction. So I start by the topic, which is modeling and control of COVID-19 epidemic through testing policies. Is the recent paper that we submitted, and my collaborators are my supervisors, Alan Kepangu and Carlos Canudas David, and two brilliant PhD students in our team, Denis Nakiting and Ludmila Tumash, and our collaborator, Pierre-Alexandre Liman from INRIA Paris. So I start with the quote of Dr. Tedros Adhanom Ghebreyesus, who is the Director General of World Health Organization. He gave a media briefing on 16 March 2020, and in which he said that all countries must take a comprehensive approach, but the most effective way to prevent infections and save lives is break the chains of transmissions. And to do that, you must test and isolate. And at the end, he says we have a simple message for all countries: test, test, and test. Okay. As an example, we look at the tests conducted per confirmed case of COVID-19 in South Korea, Germany, United Kingdom, United States, and France. And tests conducted per confirmed case is the ratio of the actual number of tests per day over the actual cases per day. And here you can see that South Korea increased their test conducted per confirmed case in March to 100, and then in April to 200, and then in May there were over 500 tests conducted per confirmed case. The second to South Korea is Germany, then comes France, then comes UK, US, and then France. Okay. So notice the pattern here. South Korea is at the top, Germany is second, and UK, US, and France are at the bottom. In the next plot, I took these plots from our World in Data website. And in this next plot, we are looking at the daily new confirmed cases per million people, which is the quantity, which is actual number of cases per day divided by the total population of that country times 1 million. Here, the list is reversed. Now, in the top, you have France and US, UK, and the second last is Germany and South Korea. So the test that South Korea was doing at the beginning and until now had a huge impact on the dynamics of the epidemic in the country. And on the other hand, France has now a lot of cases per million, and it's around 1,000 cases per million people, which is 0.001% every day of the whole population. And apart from, so testing is really important, but apart from testing, there are other policies in order to control the epidemic. Mainly, they fall into two categories. The first one is mitigation policies. They intend to slow down the epidemic, but do not stop. And usually they are implemented in order to, or in the more popular term is flatten the curve. So when somebody says flatten the curve, they mean mitigation policies. And they are usually implemented in order to limit the number of cases in order to not overwhelm the hospital capacities. Suppression policies are a bit strict policies, and they intend to stop the epidemic, or in more popular terms, it's called hammer the curve. Among many policies, they include social distancing, washing hands, like encourage people to wash hands, and then you have a policy that wear masks in public places. And on the other hand, you can have more strict policies like lockdown, travel restrictions, school closures, office teleworking, etc. And then you can have testing, contact tracing, and isolating the infected people. On the extremes, these are called non-pharmaceutical interventions. On testing, some people say it's pharmaceutical, but some people say still non-pharmaceutical because there are no drugs involved. But this problem, the extent to which these policies must be implemented in order to achieve a specific mitigation or suppression goal is nothing but a control theoretic problem. And if you want to get more how is it a control problem and how control theory can help solve this problem, I would recommend you to watch this video by Professor Steve Brunton, who is a professor at University of Washington. And he has a really nice channel on YouTube, and he released the video on May 2 about explaining how control theory can be helpful too in order to control the dynamics of the epidemic. The event of COVID-19 has motivated a lot of researchers from different backgrounds to contribute in this topic and give their perspective. And similarly, in control theory, there are a lot of papers. So in social distancing measures, how relaxed should it be? How strict should it be? So this was solved by, this was studied by Frank Algover Group and Alex Perkins and Julio Norme Rico. And basically what they did was study the social distancing measure as a control through the model predictive control framework. Similarly, Ian Craig and Fernando Alvarez, they studied optimal lockdown strategies. Francesco Casella, he answered the question if lockdown strategies can be implemented in order to control the epidemic based solely on the daily test reports. And the answer he gives is that if you are intending to do the suppression, then it could work. But if you are want to do mitigation, then there are delays involved, so you cannot achieve your objective. However, testing policies are not studied from this perspective, from control theoretic perspective. The most I found as a control theorist, Lucas Nato, they studied the test allocation problem in a population and they studied it through the sensor selection problem in control theory. And David Berger, he studied how to implement the testing policies and then isolate the infected people. But on the other hand, they will also want to maximize the economic activity. Arthur Charpentier, he studied testing and lockdown and balancing, some kind of balancing in order to limit the number of cases to achieve a safe limit in ICUs. So these perspectives are mostly based on economics perspective or optimization perspective and not really how to control epidemic. So our contribution is that we propose a CEDAR model, which has a testing rate as a control input. And then we estimate that model through to the case of France, and we validate the model on the data and estimate the parameters. And then we present two control strategies. The first one is a suppression strategy. It's called the best effort strategy for testing. The other one is mitigation strategy. It's called the constant optimal strategy for testing, or cost. So the first one is best, and the other one is cost. The remaining talk is organized as follows. So I will present the model. I will present some data of France, and then try to infer the missing data through imputations, and then estimate the model parameters, and then we will look into the study and design of testing policies, and finally I'll conclude this talk. Okay, let me look at the time. Okay. So the CEDAR model is designed as follows. The block diagram is given. Here we have susceptible population, people who can get infected, and when they get infected, they go into a compartment of undiagnosed infected, so they are not still diagnosed. So once you are infected, you can either get detected and go into a diagnosed infected compartment, or you can, if you are asymptomatic or you have mild symptoms, you don't get tested, you recover naturally and you fall into the unidentified recovered compartment. So you don't know, maybe if you're asymptomatic, you didn't realize that you got the disease and you recovered naturally. If you are detected and you go into diagnosed infected compartment, then you take some time, maybe you get hospitalized, you may be quarantined, but you are removed from the population, so you're isolated in some sense, and then you take some time in order to go into removed compartment. So why I called removed? Because either you can get recover or either you can die. So in that case, to capture both of these things, I call it removed compartment. The notation is as follows: a susceptible population at time t is xs, in undiagnosed infected is xi, unidentified recovered xu, and xt and xr. And these two compartments are measured compartments, because once you detect a person, they are recorded, like in the number of infected cases. Okay. And in the detection, we only consider RT-PCR tests, and the time, the unit of time is days. Main assumptions in the model are as follows: the total population remains constant. And then the other assumption is that the transmission of infection happens only through the undiagnosed infected. So once the people are diagnosed, they are isolated, so they don't take part in infecting other susceptible people. Okay. All the deaths due to COVID-19 are assumed to be identified and reported. So the removed compartment contains people who are recovered after detection, or people, non-survival cases, who die after getting the disease. The last assumption is that after recovery, the immunity is sustainable enough. So we assume that once you recover, you don't get infected again. So the people in the unidentified recovered compartment and the removed compartment are not infected again. So here I'll present the four outflows from the four outflows, which are infection transmission, detection, recovery, and removal. How are these models? Infection transmission is the product of infection rate times the susceptible population times the contact probability. Contact probability is the number of infected cases divided by total population, because this is a population model and it usually assumes a homogeneous structure of the population. And if you have, this is also called the mass action law, that the number of the product of the susceptible and infected population. The new infections depend on what's the value of these products. Detection is testing rate times the detection probability, and testing rate is our control input, U, and detection probability is number of infected people, undiagnosed infected people, divided by the testable population. I'll explain this testable population later, but it's given by this formula. It includes infected population and a proportion of susceptible and unidentified recovered population. Here, theta is a specificity index. Recovery happens according to the recovery rate times undiagnosed infected population, and the removal happens as a product of removal rate times the diagnosed infected population. And here we have four parameters, beta, theta, gamma, and rho, that are defined as follows. The infection rate is greater than or equal to 0. It's a piecewise constant. It can change according to the condition, external condition. It, of course, depends on the biology of the disease, but it also depends on the society, on the government's policies, etc. It is the product of contact rate, how often people meet with each other, meet with an infected person, and then it's the times the probability of getting infection after coming in contact. The testing specificity parameter depends solely on the policy, testing policy of the government. It's also piecewise constant in case the testing policy changes. So it takes values between 0 and 1. And in the extreme cases, if theta is 0, that means government is testing people randomly. Everybody is eligible who is not, who wasn't detected before is eligible to get the test. And if theta equals 1, that means the tests are very specific, meaning the government is only testing those people who have severe symptoms or very apparent symptoms. So in that case, the probability of getting a positive test is 1. Then we have recovery rate, which depends solely on the biology of the disease, and removal rate also, so we can assume them to be constant. And they take also values between 0 and 1, 0 excluded and 1 included. And 1 hour gamma is interpreted as the average time period after which a typical person who is undiagnosed recovers. Okay? And similarly, 1 hour rho is average time period after which a typical person who is diagnosed recovers or dies. And from here, we can see that the average time period after which an undetected person recovers is smaller than the average time period after which a diagnosed person recovers or dies is larger, because they are in critical condition most of the time. Mathematically, the model is given as follows. So you have susceptible population changes by new infections. So it's a decreasing function, but after a while it converges. So you can say it's a non-increasing function. And the new infections that are happening go into the undiagnosed infected compartment. From there, they get either detected and go into the diagnosed compartment, or they recover and go into the U compartment. And in D compartment, you have new detections and minus the recoveries, removal actually, and the removal goes to the R compartment. So here U is the testing rate again, and XT is a testable population. And more on this slide. Control input is defined as follows, is equal to the testing capacity per day. Either we can assume that testing, that the number of tests that are performed are actually equal to the testing capacity, or we can say that the number of tests that are being performed are equal to testing capacity, because testing capacity could be higher and the number of tests being performed could be lower, but here we assume that they're equal. And then we say that if the total stockpile of tests is unlimited, that means that new tests can be produced or bought at any time. Then we don't have to limit the total stockpile of tests. But if for some country, the total stockpile of tests is limited, they have this number of tests and they cannot buy or they cannot produce more tests, then we can write our control input as a minimum of the capacity times the remaining test, and the remaining test is defined by total stockpile minus the integral.
So I have here a question. So
yes,
how can test be an input? It's rather measurement, right? So in why CT is a kind of input, yeah? Mm-hmm.
Yes, it's not a measurement, but then when we design the testing policies, it will be an input. For the current case, if you say that France was doing these many tests, then it's a measured input.
So are you saying that by measurement you're somehow, how to say this, increasing the awareness of people to be maybe more careful, and that's how it can be seen as an input?
No, it's an input as how a number of tests you do per day. You should do per day, for example. So if you look here, so it's input in the sense that it is affecting the dynamics of the.
Okay, understood. Yeah. Mm-hmm.
Okay. So the testable population is a sample from the total population who are eligible for testing. So that means that once those who are recovered, you no more test those people who were detected before. And usually this testable population are very large than the testing capacity per day. That means you don't test all the testable population in one day. Okay. So then we have model outputs, which are measurements. So the measurements are the cumulative number of diagnosed cases, which is the number of people currently in the diagnosed infected compartment, plus the people who left the diagnosed infected compartment. And then cumulative number of removed cases, which are the people who left the diagnosed compartment and now are in our compartment. And finally, the number of positive tests per day is a third output. And that depends on the test you are doing times the probability, which is the inflow to the diagnosed compartment. Okay. This is also measured. Then we have the data, and we assume that the data equals the outputs from the model plus some noise. And then we have performance outputs, which are, the first one is number of active intensive care units, which we assume is some function of the delayed active infected cases. Active infected cases are both undiagnosed and diagnosed. And the delay is due to the incubation period plus the time that people take after getting diagnosed to ICU. So these values are taken from the literature. So incubation period is after you come in contact, how many days you take to show symptoms or to get detected. So it's usually 5 days, 5.02 or and we can assume 5. Plus after you are diagnosed, then you get hospitalized, and after you hospitalized, you get into critical situation, and then you are admitted to ICU. So normally, on average, is 12 days. So here in notation, I use B because I was for infected, and B could be beds, ICU beds or whatever. So the second one is the cumulative number of deaths, which is E, or extinct cases. It's a function of the cumulative number of infected cases. And cumulative number of infected cases is the total population minus the susceptible people. Okay. And it also depends on some delayed cumulative number of infected cases, and delay is due to the number of days that a person takes after getting in contact until dying. Okay. So you have incubation period of 5 days and then removal period of 20 days. And this 20 days is what we will estimate later in the presentation. So this was a model, and then there is a very useful quantity, which is called reproduction number. So it's effective reproduction number equals the inflow to the I compartment divided by the outflow from I compartment. So it's given by this formula. So if RT is greater than 1, that means that inflow is larger than outflow, which means the infected population will grow. And if it's less than 1, that means outflow is larger than inflow, which means infections will decrease. A more popular quantity is basic reproduction number, but it's only useful in the beginning of the epidemic, because it's used to assess the epidemic potential of a disease. But when the epidemic is in the later phases, it's no more useful. Over there, the effective reproduction is more useful. It's actually computed when replacing time at 0. And it can be approximated over beta over gamma. If the testing input at the time 0 is 0, then it's beta over gamma, otherwise it's U of 0. This quantity also appears here. So this was the model. Now we go into the data. So data is obtained from this data.gouv.fr, which is an open platform for French public data, and we have 6 classes here. The first one is the cumulative number of diagnosed cases, which is related to our first output. Number of active hospitalized, H, and ICU cases. Cumulative number of recovered cases from hospitals. Cumulative number of deaths. Number of tests and positive tests per day. And number of tested and positively tested people per day. So there is some ambiguity here, test and tested and positive tests and positively tested people. I'll explain later. So here I plot the data. So the first plot is the cumulative number of diagnosed cases. The second plot shows the green plot is the recovered cases from hospitals. So those people who were hospitalized and then discharged later. The second is from March. So hospitalized cases is the blue one. Active ICU cases is the red one. And this data is from March 17 to July 1. We don't have the data before. For the number of deaths, we have deaths reported by the hospitals and deaths reported by EPAD. EPAD is a retirement homes for old people. They started reporting the deaths in the retirement homes after April 1st. And then the total number of deaths is the sum of these two, which we denote by E bar. And then we notice a missing data here is that the recovered cases who were not hospitalized, those cases who were detected, but they were not in a critical condition to be hospitalized. So they were quarantined either in their homes or in some other facility. But we don't have data on when they recover. They are not recorded. Okay. Data on tests per day and positive tests per day. So we have 2 types of data. So from March 10 to May 26, the data was reported only from labs. And then from May 13 onward, the Public Health Authority of France PF. They installed a new system called CDAP, which were recording the number of tested people and positively tested cases. It's shown by red. And this data is complete, is from labs as well as from hospitals. And one idea we had before was that since we have this overlap of both of data, we can do least square in this overlap and multiply it by that quantity and complete this data. But there is a problem that the intensive testing policy was placed after May 11 in France. So we cannot say that France was multiplied this, and we cannot claim that France was doing 50,000 tests in March or April. So we have to find some other way to impute this data and to infer the missing data. So the first missing data is the cumulative number of removed cases. The cumulative number of removed cases are the sum of those who recover or die after being diagnosed, and you can recover with hospitalization and you can recover without hospitalization. We have data for recovered with hospitalization and deaths, but we don't have this data. The other data is number of tests and tested people per day. From January 24 to March 9, we have no data. From March 10 to 12, we have partial data only from the labs. And from May 13 to July 1, we are okay, we have complete data. And then in imputation, we try to infer the missing data from the raw data. So the first hypothesis we make is that people who recover without hospitalization divided by the diagnosed and not hospitalized is equal to the ratio of the recovered with hospitalization divided by diagnosed and hospitalized. And after making this assumption, we can compute the cumulative number of removed cases, which is the sum of people who were the cumulative number of diagnosed people who recovered with hospitalization and those who recovered without hospitalization. And then we're using this hypothesis, we can compute it as this. So this Y2 bar is people who recovered with hospitalization. And Y1 is the cumulative number of diagnosed cases. So we know all these quantities, we can compute the cumulative number of removed cases. Then for another hypothesis we make is the test per day equals tested people per day, because no person is tested twice per day, we assume it. And then similarly, positive tests per day equals the positive cases per day. For January 24 to March 9, there were not many tests being done in France, so only those people with the apparent symptoms were tested. So we can assume that the number of tests done during this period equals the number of positive tests, because not many tests were being done at that period. And then number of positive tests can be computed by the forward difference operator of number of diagnosed cases. So if we take so number of confirmed cases that day equals the number of positive tests that day. For March 10 to May 12, we have the data from the laboratories, and we assume it that is equal for that period. And for the positive cases, we again do we don't have the data from the hospitals, so we assume the number of positive tests equals the daily positive confirmed cases that day. And for the third period, we have the data, so we don't need to do imputation over there. After imputation, here I plot the data. So the first output is the cumulative number of diagnosed cases. The second is the removed cases. And then we have positive tests per day. And this is the input, which is number of tests performed per day. Okay. Using this data now, we'll estimate the parameters of the model. So first one is easy. one, which is the removal rate. We just use the relation of the model, and using this relation, so XR is Y2 and XP can be obtained from Y1 minus Y2. Then we do the approximated by the discrete difference operator, and then pose it as least square estimation problem. So we subtract this minus this and try to fit this both of these signals with each other using the best possible rho. And this gives the solution using the least square formula to be equal to approximately equal to 0.05. And from here, we get that the removal period would be 1 over 0.05 is approximately 20 days. Then we have three for infection and recovery rates in France. We realized three phases in France during January 24 and July 1. So the first phase is before lockdown, the second is during lockdown, and third is after lockdown. Since our infection rate is piecewise constant, we assume that in each of these interval beta is constant and beta changes when the condition change. So from January 24 to March 16, we have beta 1. Then during lockdown, we have beta 2, and after lockdown, beta 3. And recovery rate, we assume it to be constant. Testing specificity parameter depends on the testing policy, and again from our world in data you can see that the testing strategy in France until May 10 was that only symptomatic people and key groups like old people or people with diseases, you also had to have prescription from the doctor to get the test. But from May 11, anyone with symptoms could go and then get tested. So due to this change, we assume two values of theta. And then the problem of estimating beta, theta, and gamma is posed as follows. So we define this parameter vector, and the optimal parameter vector would be the one minimizing the cost function. And the cost function is the model output minus the data. Whole square. So we have three outputs, and from January 24 to July 1, we take all the data and minimize this. And this can also be solved by least square, but it's not recommended because the parameters are the output is not depending directly on the parameters, but through the solution trajectories of the model. So so also there is you have to take the double derivative of the data, which would amplify the noise, and also the gradient descent algorithm is could be also not easy because of computing the gradient. So we employ the derivative-free algorithm, which is particle swarm optimization, a very powerful algorithm, and then estimate the parameters, which is as follows. So beta 1 is around 0.37. Then during lockdown, it drops to 0.07. Then we have beta 3, which is again 0.37. And theta 1 and theta 2 change slightly. And finally, gamma is 0.1589, which tells that 1 over gamma, which is average recovery period of undiagnosed infected, is around 6 to 7 days. Here we plot the model outputs and show that it matches the data very good. So here we have cumulative number of diagnosed cases. The blue line is the data. The red line is the output of the model. And then here we have cumulative number of removed cases. Here we have number of positive tests per day, which is very noisy, but model follows it. Just here there is mismatch, but overall it's a very good fit, the model. Then we have performance outputs of active ICU cases and the number of beds. And we would like to plot the data of active ICU cases with the predicted number of active infected cases of the validated model. And then we fit this data with this function, which is the red one. So it's a polynomial fit. And then here we plot with respect to time, the actual number of ICU patients and the predicted number of ICU patients. Similarly, we do it with the number of deaths and infections. So we fit the data with this function and then plot it with respect to time. Finally, we'd like to show the effect of lockdown in France. So the lockdown was placed on March 17, and it decreased the diagnosed population. So the number of people who were detected. And if the lockdown wasn't placed at that time, if we had the same beta value, then the infection would grow like that, this blue line. And then on May 11, the lockdown was lifted and the rate of decrease slowed down. So, and if it wasn't lifted, then the cases would be decreasing at the same rate. We also computed the reproduction numbers from the model. So R0 during the outbreak was 2.33, computed from the model, reported by French government. So they don't consider any model, they compute it from the data. It's the number of cases in this week divided by number of cases in the last week, like the moving average, and then they estimate in a very crude manner. So they estimated 2.7, our was 2.3, which is not very far. And before that lockdown, at the end of lockdown, the effective reproduction number was 2.3. And during lockdown, it fell into 0.33. Here they say it's 0.7. But after lockdown, on July 01, it was around 1. And here it's also around 1. So the final part is the design of testing policies. The first policy that is a suppression policy is defined as follows. So first we say that the epidemic is spreading if the infected population is increasing, the undiagnosed infected population, which means that the effective reproduction number is greater than 1. And then we say it's non-spreading if the infected population is non-increasing. That the reproduction number is less than or equal to 1. So the best effort strategy for testing policy provides the minimum constant testing rate from the day T star onward, which is required to switch the epidemic from spreading to non-spreading. So this policy is only meaningful when the epidemic is spreading. So it helps to stop the spread of the epidemic. So how is it, how can we compute it? So in this proposition, it says that assume that beta doesn't increase and the theta doesn't decrease. Then on some time interval, then we can say that the best effort strategy at time T star is given by the testing rate should be greater than or equal to C star at T star. So it's a constant. This is some function computed at T star. Here, the notation, this plus with plus says that if this quantity is positive, then take it as whatever the value is. If it's negative, then take 0. Okay? So that means that if the epidemic, this quantity is negative if the epidemic is decreasing. So if the epidemic is already decreasing, the best policy says that the minimum you can do is 0 tests. The proof sketch involves in making choosing the value of u of t such that the xi dot t is less than 0. However, at T star, we are changing the value of u of t. So there is a discontinuity at T star. So we cannot prove it through the derivative and taking the second derivative and showing some kind of concavity at t star. So we consider this function c of t, and the lemma says that if u of t is greater than c of t, then we show that xi of t is decreasing. If it's greater than equal to c of t, then it's non-increasing. And then we want to prove that if u of t is greater than c star of t star, then this still holds, xi of t is non-increasing. So first we note that the susceptible population is always non-increasing. And then we show that if the input is greater than equal to c star t star, the best policy, then the testable population is also non-increasing. Okay? And then when we have that, the testable population is non-increasing and the susceptible population is non-increasing, then we can show that if our testing rate is greater than the best policy, then we will have, we can show that the u of t is greater than this function. Okay? So since here we showed that if this u of t is greater than equal to this function, then xi is non-increasing, then we prove it. Then the best policy holds. So finally, we ask the question if the number of tests required by the best effort strategy for testing is realistic or not. So we plot here the number of tests required by the best policy with respect to time, and then we also plot the corresponding peak value of the infection. And here I see that currently, as of today, France is doing over 300,000 tests per day. And the best requires from January to like at the end of February, it is requiring around 70,000 tests per day. But if applied from March 01 onward, it would require 147,000 tests per day. So it's not very unrealistic number. In the evaluation, we show how it changes the course of epidemic from spreading to non-spreading. So in the red, we have the original dynamics, the predicted dynamics of infected cases in the actual testing scenario of France. And in the green, we apply the best policy at March 10. And here we note that the diagnosed population will not stop increasing at t-star because xi is stopped increasing because we are putting all the detected population in the D compartment. So it will increase, but it will be lower than the original case. Then we plot the predicted number of ICU patients, P, with actual testing is the red one, with the best policy is the green one. And we see that the peak value of the ICU patients, active ICU patients, decreased by 35%. And the total number of deaths at the final value decreased by 75%, which is very significant. The other strategy is a constant optimal strategy for testing. It's a mitigation strategy. It doesn't stop the epidemic, but it slows down the epidemic. And it is the optimal allocation of tests along time. When you have limited stockpile of tests, you cannot produce tests afterwards. So you have limited number of tests that you have to utilize, and you have to utilize it optimally. Some sense. So the definition is as follows: that the cost policy assumes that the total stockpile of tests is limited. It's given by RMX, and the input is constant until the test finish. So they will finish on RMX divided by C at time equals to RMX divided by C. So you do tests per day, C tests per day, until this time, and then afterwards you don't have any time. And you have to choose the C such that it minimizes the peak value of the infected population. However, there is a spoiler, there will be two peaks. Okay? The first peak occurs when you're still doing testing, and the second peak occurs when you stop testing, and there will be a second wave of the epidemic because you don't have any more tests. To show that so here you are doing testing, but then you finish your tests here, somewhere here, then you have the second wave of the epidemic. Okay. So there is now the game of finding the optimal. So if you reduce the first peak by doing a lot of the tests, that increases, you will finish your test very soon. It will increase the second peak. Okay. But if you want to decrease the second peak and doing very less tests in the beginning, you'll have very high first peak. So another spoiler is that optimal testing happens when both peaks are equal. Okay? So we have to equate these both peaks. So first we need to find the solution of infected population. We change the time scale of from time t to xi. In this manner, so xi is actually the integral of xi t dt. And in this time scale, we can write the solution of the infected population as follows. So xi star is the horizon of testing. So it's the equivalent of stoppage time capital T in the infection time scale, xi. So before xi, the solution is given by this, and after xi, the solution is given by this trajectory. And here we assume that the testable population is constant, and we will validate the model with this assumption later. Because if we don't make this assumption, then the differential equation of xi becomes the Abel's equation of second kind, which doesn't have a solution, analytic solution. So this assumption is necessary. Then we do the analysis of the evolution of the infection peaks. So we take the derivative of with respect to xi, equate it to 0, and then we obtain this peak times. The first one is less than the second one, and the stoppage time occurs in between these two times. And this RC and RW are two reproduction numbers. The first reproduction number is RC, which is the, when you are doing testing, what is the reproduction number at that time? And when you stop testing, what's the reproduction number? So these are basic reproduction numbers, not the effective ones. And then putting this xi values in the solution trajectories, we get the infection peaks. Okay, so the peak value, first peak value would be equal to this, second peak value would be equal to this. Now we equate these two values. So, and the optimality condition here is that the peak of infection is minimized when both of these peak values are equal. Okay, and from here we obtain the stoppage time. Equation of stoppage time and the equation of the optimal number of tests of the cost policy. And to write these equations more explicitly, we have a proposition here. So we write the same equations, but in a more explicit manner here. So the cost policy C is obtained by solving this system of equation where we have two unknowns. The first unknown is C, the second is the stoppage time xi star. And this system of equation doesn't have analytic solution. So we solve it numerically using Newton method, for instance, but any method can be used. So once we compute C, we ask again the question, how many tests are required by cost policy? So here in blue is the actual testing from the data. And the green one is around 17,000 tests per day, and from January 24 to May 28. We keep the total number of tests, the total stockpile of tests, same in both scenarios. So in the blue case, the integral of blue is equal to the integral of green. So you say if we have the same number of tests that France did from January 24 to July 1, if we do it, allocate it more optimally, what we get. Okay? So after May 20, we finish our test. We don't do any testing in this period. So remember, we made an assumption that the testable population is constant. It turns out that even if you assume this assumption of the testable population being constant, we can still validate the model, and the validation is shown here. You have fitting of the model in the log scale, all the three outputs of the model. And then we thought, again, do the fitting of the ICU patients and cumulative number of tests with this red plot. And the green plot is the one with the cost policy. And here we show that the peak of the active ICU cases decreased by 11%, and the total number of tests are reduced by 38%, which is still, again, a significant number. In conclusion, we propose a CEDAR model which has testing rate as a control input. That means testing can directly influence the infected cases or the dynamics of the epidemic. We estimated and validated the model on French COVID-19 data, and we proposed two testing strategies to control the epidemic. The first one is the best effort strategy for testing. It's a suppression strategy because it stops the epidemic on the same day by doing testing from that day onwards. Cost policy is constant optimal strategy for testing, is a mitigation strategy. It wisely allocates the total stockpile of tests along time in order to minimize the peaks of the infection. The future work involves to combine the serology tests. So serology tests are blood tests that detect antibodies in the serum, and that confirms if you were infected in the past or not. And they are also very important because they reduce the size of the testable population. So once you detect the person who was infected in the past, so you don't do RT-PCR test on that person. And in this way, you increase the probability of detection, and you can be more efficient with the RT-PCR test then. The second is the observer design for the CEDAR model, because right now we predicted the undiagnosed infected cases, but they may not be real, not the true values, because we don't have any feedback mechanism of the observer. The third would be to propose dynamic testing strategies, maybe in finite horizon or infinite horizon. Here we didn't do dynamic because we wanted to make it as simple as possible to present some testing, because that's what the governments or public health authorities do. They specify the target that these many tests per day we have to do. And it's not, so the dynamic testing policies, even though they're more interesting from control theoretic perspective, they could be complex or difficult to implement in reality. So if you have any questions, I will be very happy to answer them. And finally, I would like to acknowledge that this study was supported by European Research Council under the European Union's Horizon 2020, and also by INRIA in the framework of COVID-19 Fast Track Research Program. And the data and all the codes are available in our group website, which is Scale-FreeBack.eu /COVID-19. And you can also contact me if you have any questions through email.